Hello, everyone. Thank you for being here for this talk. My name is Kostas. I'll be talking about the work that we've been doing at the University of Rochester with my advisors, Shen and Michael Scott, on enabling operating systems research by inferring interactions in the black box GPU stack. So let's start by taking a look at what we're actually referring to here as the GPU software hardware stack. It is composed out of three basic building blocks: the GPU hardware itself, of course, the GPU driver, and libraries like OpenCL and CUDA that application programmers use to access these devices. There are two basic problems that appear in this picture, and I'll detail them right now. First of all, it is the very fact that these components are represented in black, exactly because vendors provide us with GPUs in the form of black box stacks. They give us binary drivers, binary libraries. They give us little to no documentation about how these systems are supposed to work together and how they are supposed to be implementing resource management. Moreover, if we look at the shape of the library black box in this picture, we can observe that it allows an application to directly access the hardware to pass an acceleration request. This is a performance optimization put together so as to avoid the cost of tapping to the kernel, especially for very low latency requests. That means that given these two basic problems, it is impossible for the operating system to know who, how, and when is actually using a very precious processing resource in the system. So we are suggesting that it is possible to build kernel-level schedulers for GPUs without necessarily opening these black boxes by inspecting these cross-black box interactions, understanding and building upon them. So we want to build GPU schedulers at the kernel level, exactly because this is a level at which we can offer a certain amount of protection guarantees impossible at the user level. And moreover, because we can coordinate resources, the different processing resources of the system, to achieve system-wide scheduling objectives otherwise unattainable. By working with black box GPUs, we should be able to be working at the cutting edge of the feature set that vendors provide us with, as opposed to working with open source alternatives, which unfortunately have to stay 1 or 2 generations behind until they catch up in their reverse engineering effort. By enabling application programmers to understand and reason about performance anomalies as they occur, for example, due to contention or unrealized system interactions, we should be able to offer a significant level of understanding about where exactly these performance anomalies stem from. And last, by discovering an event-based interface at this level, we should have a unique solution that should apply regardless of whether the GPU stacks are provided to us as white, gray, or black boxes. So we want to systematize a methodology to uncover and understand black box interactions. We do not promise miracles here. We will be limiting the reverse engineering effort in its scope and how hard it is, but we cannot eliminate it entirely. We will be aiming at producing a state machine that describes how the GPU software hardware stack works. Working with a state machine makes it possible to actually discover its interactions without prior knowledge about their meanings. Moreover, having a state machine provides us with a simple and concise description of how such an artificial system, a man-made system as a GPU software hardware stack, actually works. It is a human-made system. It should be following a blueprint of appropriate behavior. And last, if we are able to enable the operating system kernel to intercept and intercede on scheduling-related events, we should be able to enable scheduling of GPU requests. By GPU requests here, I mean the set of operations that run on the GPU entirely uninterrupted. And this is the minimum schedulable entity that we care about from the system's perspective. So here's very quickly how we're going to go about learning these black box interactions. First of all, we're going to start by collecting detailed event traces as they occur across all the interfaces. For example, at the API level, we might implement techniques like DLL redirection to capture all API calls as they occur. At the memory hardware interface, we might implement techniques like fault injection to capture every memory access to every GPU mapped memory buffer that occurs through an application that is accessing the hardware. Having these detailed event traces, we're going next to simplify them. We're going to map them to a smaller equivalent set such that we don't have to apply our inference on a very large number of symbols. we will be using language inference as a technique that will allow us to automatically infer the state machine that governs how these traces must have been produced. And having the state machine, we're going to apply some limited reverse engineering techniques in order to identify the structures and events that are actually used to pass scheduling-related requests to the system. So here's an example of how the traces that we have to deal with look like. On the left and the right, you can see two sample traces. The events that appear in the traces have been simplified in a way that every event is actually a unique symbol. So if we consider each trace to be a collection of symbols, we can consider it as a word. And since every trace is a word, and this is a word of an unknown language, then we can infer its grammar and describe the language that describes this particular language through its state machine. For example, the machine that accepts the two samples in this picture is presented right below them as a non-deterministic finite automaton. We work under the assumption that the GPU state machine can be described by a regular language, and as a result, this language should be possible to be automatically inferred using DFA inference. So we're trying to infer this language, and we're trying to build a state machine, and it would be trivial to build a state machine if we just started with a start and an end node, and we just marked a path between the start and end node that contained the words that we were given as input, which is actually our traces. Of course, such a state machine would contain so many states and so many events that would actually be unreasonable to convey any information. So we would like instead to minimize it, to produce a state machine that contains the minimal amount of information that a human can understand, but yet still presents and represents the exact same language. For this purpose, we use state machine reduction, and in particular, we select to use the k-tail state merging algorithm. I will not be getting into details about how the algorithm works, but in principle, it merges states for which the acceptable length k or shorter future events are the same in the order produced by the DFA. So, excuse me, are the same in order to produce a DFA. The DFA that the algorithm produces is actually the precise description of the state machine that governs the input. The difference is that in practice, we don't necessarily have the amount of input that the algorithm requires. So instead, our implementation produces the equivalent and mostly informative NFA. Since it is easier to analyze a deterministic finite automaton, we add an extra discretization step that merges states that are reachable from the same preceding states by the same event to produce a final solution, a deterministic finite automaton. The k-tail state merging algorithm can be affected in its efficiency by the value of k. We are not pre-selecting the value of k. We are actually running the algorithm for multiple values of k, and we use a simple rule, we use a simple set of rules to actually define the value of k that will give us the state machine that we want to analyze. This simple set of rules includes, first of all, to avoid the extreme values of k, because such values of k do not necessarily carry through the state machine that they produce relevant information. They tend to produce over or under merged state machines. And then pick a case as a small variations in its value will not alter the graph's complexity. That means that the end graph that will be produced will contain mostly the same number of nodes and edges. By this simple set of rules, we have a smaller set of state machines to analyze and pick a k from, but we still, since they are mostly similar, we still would like to pick, with a certain level of intuition required here, one particular machine to analyze. In this case, we select the smallest non-trivial machine that fits in this set, that is one with cycles rather than long straight paths, as long straight paths tend to be the result of imprecise state merging. So in the figure that you can see at the bottom of this slide, we have presented how the value of k affects the complexity, the number of nodes and edges that appear in the graphs in our system for the 3 Nvidia GPUs that we have got to work with, spanning 3 generations of Nvidia GPUs, and for an input of 5 traces of 5 to 9,000 events. We have marked with a dot the values of k that would signify the particular state machine that we would choose to analyze. This is a sample output of the actual algorithm, one of the state machines that we actually have to analyze. It is in particular for for the NVS295, one of NVIDIA's first fully programmable GPUs with respect to its CUDA capabilities, and produced for a value of k equals 35. Now, I understand this graph is probably too hard to analyze, especially in the next minute, so I will just point your attention to how we're actually using this graph. And the way we use this graph is actually as a map to guide our attention to particular parts of the trace that we have collected that should be carrying the most scheduling-related relevant information. So, for example, on the top right of the graph, there appears the entry node, followed by a green edge, and we have marked with green color the equivalent type of edges that appears in circles following the entry of the graph. When we look back into our traces, we realize that this set of events tends to be related to creation of new memory buffers. And thus, when we stumble upon such events, again, further down in our traces, and in particular, for example, in loops that appear on the up left corner of the graph, we know that they can be correlated with this specific functionality, and we can put them aside for the rest of our analysis. If you can see the brown edge on the graph, it belongs in a loop which contains continuous and subsequent reads and writes to perfectly identifiable memory areas. If we inspect back into our traces, we realize that the frequency at which this loop appears follows the frequency at which API-level events that carry information related to making new requests appear. So we can correlate the two events and realize that actually it is writes to specific memory-mapped registers that carry the information of making a new acceleration request to the GPU. Let's look at a more distilled, boiled-down version of this state machine as it has been produced manually by merging the information that we have gathered for the 3 GPUs that we have worked with. In this particular case, we have produced a state machine with a small number of states that actually describes how uniquely identifiable buffers are built and used through the lifetime of the GPU accessing application process. The state transitions through which this state machine goes are stemming from API calls that are made by the application using the accelerator or the hardware of the GPU. Since it is possible to capture and intercept all events that appear in the traces, in particular, it's possible to capture and intercept all events that appear in these edges of the state machine, we should be able to hook up an event-based scheduler on the particular edges that mark the creation and completion of a new GPU request and be able to schedule it at the operating system level. So in summary, I have presented how using classic state machine inference, we can semi-automatically infer a meaningful GPU state machine. Through safe and protected kernel-level scheduling for black box GPUs, we can, by intercepting and acting upon uncovered events, enable features that are currently missing in systems like fairness and protection. Commonalities in the GPU software-hardware stack, and namely structures like the GPU ring buffer, make us hopeful that the methodologies that we present here apply in general across different libraries, vendors, and devices. We are currently in the process of validating with open alternative stacks and utilizing uncovered semantics to drive interesting GPU scheduling. We have what we believe to be interesting results in terms of fairness and performance, and we look forward to be presenting them to you soon. So with that, I'd like to thank you and open up for questions.
Okay, I'll ask a question. So, I guess my question is really, did you talk with Nvidia? I mean, another way to get this information is to ask them, right? So do you think, they would just give you the information, or
no, I
they
guess
want
that
to
is
keep...
I guess that is wishful thinking. I mean, I'm afraid that the reason that these GPUs appear as black boxes is very good. They have been built in a way that they are particular examples of co-design software and hardware. By sharing information that we're trying to uncover through such processes, we're asking them to share IP that they are very protective of. Now, of course, under market pressure, they might at some point decide to share such information. But much like many parts of the technology that we have to deal with, we want to be able to guide and enable systems research on such devices right now, rather than wait for that optimum time that they decide.
So without wanting to get you into trouble, can you from what you learned so far, what would be some information that you got that you think would be...
Oh no, this is not information that given that this is all the clean room reverse engineering, this is not information that is not necessarily possible to get out there, right? I stay at the most shallow level of the clean room reverse engineering that is required to infer these interfaces. We have been tagging upon the structure a main structure of the GPU, a producer-consumer mechanism that is called the GPU ring buffer. I think in this very same conference, people have talked before about how it can be used in open source alternatives, through open source alternatives, to guide scheduling to the GPU. The problem with that is that when you limit yourself to such solutions, you cannot, for example, have the last set of CUDA implementations or any OpenCL implementations. That is critical for the type of inputs that we care about, and is critical for as a representative type of inputs for future systems.